As you can see from the content of the presentation, some objectives, some constraints, technical framework, development and implementation, challenges, and the next steps. Okay, starting with the objectives, as I've already said, we'll try to adapt and integrate into COALITON-4 the weather products for the Romanians for the Romanians case, because this model was developed by the MeteoSwiss team from Switzerland. And yeah, we'll try to do this for the Romanian's case. We'll try to create a high precision system for between 0 to 1 hour predictions of heavy rain, hail, and lightning. We'll integrate, as for the data sources, we'll integrate radar, satellite, lightning, numerical weather prediction, and digital elevation model, all for Romania's case. Okay, so we'll try to also document and adapt the adaptation process and publish the code as well on the MeteoSwiss GitHub, because we had an agreement with the MeteoSwiss team. So we had to all we will be doing for on the code base. We had to publish it as well on their GitHub. And we'll also try to evaluate alternative AI nowcasting models, because this is a nowcasting model, alongside COALITON-4 implementation, because we can see that with each, let's say, month or so, another model appears or method appears, and it may be even better from the ones we have until that point. So yeah, this is to be seen in the next months. Okay, some constraints, of course. We'll try to. This is the main constraint: adapting these data sources, because, for example, we want to integrate for the satellite data. We are currently using Severi, which is from MSG, the previous generation satellite data, and we'll try to integrate FCI, the data, which is the next generation imaging instrument, which is on board of the MTG satellite. This is one of the constraints, and we'll try to look into that in the future. Of course, numerical weather prediction archives, the limitations include things like the archives are should be pre-processed before use, before they can be used, or they are extremely large files, and this can be a problem for the processing part of the model. And of course, some radar product constraints, because some of these products were, let's say, have to be combined to get what we need, or some of them we don't really have, and we have to kind of compute them manually ourselves, compared to what the MeteoSwiss team used. Okay, again, as for these data-driven models, we have challenges concerning the extreme weather events, capturing extreme weather events, because they are, in most of the training data sets, they are underrepresented, and in the future we'll try to mitigate this situation by including, we'll see in the future slides, by including a hybrid approach, another model, but a physics-based model. Okay, and of course, as for the, as I said, for the Romania's case, the model was first trained on the extent of Switzerland, and this is the main challenge for us to adapt to the topographic and climatic characteristics of Romania. And of course, the main solution to this is model fine-tuning. Okay. For the technical framework, I've listed here what we used as part of the hardware, software, and a little bit of the model description. So we have the model itself is a recurrent convolutional, uses a recurrent convolutional architecture. It's an encoder-decoder structure. They say encoder forecaster, so it's the same thing. Okay. For multi-hazard nowcasting, again, they predict lightning, hail, and precipitation maps. As for the hardware we used, we have in our workstations at NMA. Yeah, you can see what's the most important part here. The most important hardware piece is that we have RTX 6000 GPUs, which are pretty powerful. They have like 50 gigabytes of VRAM, and that's good because we can train the model efficiently this way. And of course, the RAM, we have some workstations which go up to 256 gigabytes of RAM. Okay, as for the software stack, we used Python 3.12.4. TensorFlow, it's an older version of TensorFlow because it's like 2.9, if I remember correctly, because as let's say the first things that I discovered, and I discovered in the hard way, was that the model, I use a newer version of TensorFlow, and I got a lot of errors because of that. And unfortunately, the model is not really well, even the code base is not really well documented. And this was a problem because I didn't really know what I had to pretty much trial and error all the versions of the available of the necessary libraries to get the model working in the first place. Again, we use Xarray, which is a library used to handle the NetCDF data, because all data, as we will see in just a minute, all data sources will be in the NetCDF format. And we can handle them efficiently with Xarray and Dusk as well, because Dusk will be used to handle the scenarios where we have run into the memory more than the capacity of the memory data, which is higher than the capacity of the memory. And Dusk, pretty much what it does, it can run the model, train the model, and handle the data so the process doesn't crash. Okay, so this is the most the simplest way to explain it. Of course, we'll use scikit-learn. We'll see in just a minute where we used scikit-learn, and CuPy for GPU accelerated processing, because we used that as well for processing the heavy mathematical computations, because on the CPU would have taken too long. Okay. The data processing, as I said, leverages the GPU acceleration to efficiently process 5-minute temporal resolution data. We'll start, the model was between 0 and 1 hour in advance prediction. And we started with 5-minute temporal resolution data. We started at 5-minute temporal resolution for the initial part of the development, and as you can see, from their paper, because the model has a paper associated with it. Okay, demonstrated that the short-term forecasts were the most valuable data source for these forecasts were the radar data. So yeah, this we looked into it, and it's true. This was the most useful data source. Okay, this is the architecture. they used, the COALITON-4 architecture. Not much to say here. As I've said, an encoder-decoder architecture. They used past and future inputs at lower and higher resolutions. For the low resolution, they used residual connections, and for the future inputs, the high resolution inputs, they used downsampling. And of course, everything is incorporated into the recurrent connections. Okay. Going further here, okay, we have the data sources. So as I've said, the data sources are radar, numerical prediction, satellite lining, and digital elevation model. All of them, not all of them, but most of them were in different file formats, and we had to transform it into the NetCDF format. Okay. So as you can see, for the radar, we had 7 sites in NMA's network, the Leonardo weather radar network. This is how we got the data. For numerical prediction, we used the icon model at 2.8 kilometer spatial resolution. For the satellite, these were the first ones that were different from NetCDF. They were NAT files, which we converted to NetCDF. They come from Severi in first place from MSG. Then we'll use FCI from MTG to collect them. Okay. The instruments that they were collected from. Let's say that. Okay. And yeah, these data were from had the spatial resolution between 0.5 and 2 kilometers. For the lining data, these were KML files. These were CSV files, let's say, that these were not maps. These were the first data type that was not a map, a matrix, let's say. These were points in a CSV file that we had to create as maps so we can fit to the model. These were gathered using 9 sensors in the NMA's network, the lining detection network. And as for the digital elevation model, these were GOT file converted to NetCDF as at 1 kilometer spatial resolution. Okay. As for the development and implementation part, the MeteoSwiss team used their projection of Switzerland, and we had to change that with Romania's stereographic 1970 projection, which is referenced as with the APSG code you can see on the slide. And this code defines the spatial reference system that is that's the most fitting for Romania. The most fitting for the Romania's projection, as we'll use the this projection for the coordinate system. The latitude and longitude. We need latitude and longitude values, and this was the most fitting projection. And we also included, we will see in just a second, an image, 256 kilometer buffer zone around Romania. So it's not fitting just Romania, and it also fits the a larger, let's say, zone, because this way we want to prevent the boundary effects that may appear from the patch creation process. Okay, you can see that then data was transformed, as I said, from GeoTIFF to NetCDF. We calculated terrain derivatives from altitude data, east, west, and north-south slopes. Lining data converted from KML to NetCDF. We generated binary occurrence maps at 10-minute intervals, and current weighted and density maps at 5-minute intervals. This was also stated in the paper as well. Okay, the 12 satellite products were acquired from the MetSat data store, of course, captured by the MSG using the onboard Savvy instrument and processed into standardized NetCDF format. For the radar data, with the 7 sites, we gathered the the data as I've said at 5-minute interval for all the products. As for the numerical weather prediction products, we used Icon instead of Cosmo because it's the newer model and the better performing one. The MeteoSwiss team used Cosmo for their numerical weather prediction products used in the training of the of COALITON-4. Yeah, and this is the data part. We can see here, this is the projection we used for Romania. It also captures Moldova, Serbia, Bulgaria, Hungary, Slovakia, part of Ukraine. So yeah, it's this is to try to mitigate that problem. If we get patches for Romania, if we had a smaller area, we would not, we'll probably not be able to capture all of the necessary terrain to train the model efficiently. Okay. For the next part, for the patch creation and code optimization, we did that as well. We optimized some parts of the code. We used we identified the storm cells in the radar data using the dbScan clustering algorithm, and we extracted the 256 by 256 pixel patches. This was the first. The first step. Then we aligned all the data sources with, as you saw, with different spatial resolutions, and we used GPU accelerated acceleration to create these 32 by 32 patches, and a part of the code, let's say the main function that did this, is in the right part. So we tried to, them being a different spatial resolutions than the radar data, all the other data, so NVP, DEM, lightning, where had to be, let's say fitted into the radar resolution. So yeah, they had to be let's say approximated. And on the CPU, we tried on the CPU, it was way too slow, and we this is where we used the CuPy to put all that effort, that calculation effort, on the GPU. As you can see, we tested this, and we measured this time, and was almost 1.5 times faster. Again, with different parallel CPU operations for the creation of the NetCDF files, as I said before, and with the GPU acceleration, it was like 1.5 times faster. Okay. We also explored some SVD-based dimensionality reduction and truncated metrics approximations, so we can have an even faster, let's say, pre-processing all of these data products, a faster calculation of all of these data products. And yeah, this is, we have to conduct an analysis of these approaches, because of course, as you can guess, the approximations, any approximation is means loss in data, so loss in, of course, in accuracy for the model, and yeah, we'll have to conduct future experiments for these ones. Okay. these are some patches that will be fed to the model for the training phase. Some patches for the RZC patches from the radar, some DEM patches. On the OX axis, we have the dimension, and on the OY axis, we have the number of patches that were created. And these were like these were created using their code. So this was the code for the patch creation was not modified. And there were like, let's say, averaged. All the patches were something like averaged together to create these maps that will be fed into the model. And as you can see on the colored scale, we have their respective values, what the true values are. And for the DEM patches, we can see that we have being altitude in meters, we have between 200 or so, 233 to almost 1900 meters in altitude. Okay. For the challenges, yeah, as I've said, converting all these data products into the standardized NetCDF format was a little bit of a challenge because of the data volume and or the necessary, let's say, efficient steps we had to implement to calculate these, okay, to compute these. And of course, with consistent spatial resolution, because as you saw, they all had different spatial resolutions, and this in itself is a challenge that it's hard to, yeah, it's hard to accomplish, to mitigate, because in this step we had data, we will have data loss, and this is a problem. Okay. As for the planned MSG to MTG transition, this is again will require processing pipeline modification. And as for the numerical methods, as I've said, all these approximations will require a balance, an analysis to check the balance between the computational efficiency and the forecast accuracy, because again, in the data loss department as well, let's say. Okay. As for the next steps, we will try to integrate the remaining data, because radar and numerical order prediction data, because at this point, as I've said, this is a work in progress, and we integrated most of the data, but we had these ones to integrate into the model as well. We will fine-tune COALITON-4 after the integration of all the data the weather products to adapt to the Romania's weather patterns. We'll analyze some product, the impact of all the weather products, and potentially we'll try to exclude the ones that are not as valuable for the model, and why not include ones that may have a better impact on the accuracy of the model or the forecasts. Yeah, we'll have to do this as well. As I've said before, we'll try to replace the MSG data with newer MTG satellite data. We'll try to develop a physics-based model to complement the COALITON-4, because as I've read through the papers, the recent papers, in the last 2 years, the hybrid approaches were the most, let's say, the most competing ones, because you can have a bigger model, a world model, as NVIDIA and Google and other, and even Microsoft had developed in the past. But for the case of specialized on certain regions, models specialized for certain regions, we had to scale down the model, and for this to work, we have to get a more smarter, let's say, approach, and this is one that looked the most promising from the papers I've read, the hybrid approach, where we included a physics-based model. And of course, we'll try to evaluate the data processing pipeline for optimization needs in the future, again with GPU operations, parallel processing, and probably, why not, numerical approximations. And yeah, that's all from me. If anyone has any question,